Hi friends, last class we discussed about imaginary number and its definition. Imaginary number, it is denoted by I, is nothing but square root of -1. Today we are going to discuss one of the property of imaginary number. The sum of four consecutive powers of I is 0. We'll try to prove the statement. For example, I am taking I raised to n plus I raised to n plus 1 plus I raised to n plus 2 plus I raised to n plus 3. We find out what is the value of these four imaginary numbers whose powers are consecutive numbers. For example, n, if you feel it as 90, it will be 91, it will be 92, it will be 93. So we know that 90, 91, 92 and 93 are four consecutive numbers. Now, can I write it as I raised to n by using exponent laws, that is a raised to m plus n is a raised to m into a raised to n. By using that property, can I write it as I raised to n into I raised to 1. In the same way, it can be written as I raised to n into I square plus I raised to n into I cube. Now, we can take common I raised to n. When you take common I raised to n, we will get 1 here plus I square plus I cube. We know that I square is nothing but -1 and I cube is nothing but -I. We discussed it in my last class. Now, by replacing those values, I raised to n into 1 plus I. In place of I square, I can write -1. In place of I cube, I can write -I. Now, while observing here, -1 and +1 get cancelled. Positive iota and negative iota get cancelled. So finally, we got I raised to n into 0 is nothing but 0. So from this, we can able to understand that the sum of four consecutive powers of I is always 0. We will do one problem on this. For example, I want to find the value of I raised to 150 plus I raised to 151 plus I raised to 152 plus I raised to 153. We know that here 150, 151, 152, 153 are four consecutive numbers. So by using that property, we can write directly the answer is 0. Or else we can take it as 150 plus, or if we forget about that property, we can write I raised to 150 plus I raised to 150 into I raised to 1 plus I raised to 150 into I square plus similarly I raised to 150 into I cube. Now if you can take common I raised to 150 as common, you will get 1 plus I square plus I cube. This value is 0. So 0 into anything is 0. I hope it's clear. Now, we will discuss about the further concepts. Suppose I am taking square root of -4. Can I write it as square root of -4 can be written as 4 into square root of -1. We can write it as square root of 4 into square root of -1. So can I write it as 2i? Because square root of -1 is I, square root of 4 value is 2. But square root means you have to take plus or minus. Please remember this. Now, what I am going to explain here, if suppose A is a positive number and B is also a positive number, then square root of -a we can write by using the above property, we can write square root of A into I. Similarly, square root of -b can be written as square root of b into I. Now, for example, square root of negative a, we wish to multiply by negative b. Can I write it as square root of a into I square root of b? We know that square root of a into square root of b equals to square root of ab. By using that property, can I write it as square root of a b into I? But I is nothing but square root of minus 1. So, can I write it as square root of ab into minus 1? It is nothing but square root of minus ab. Now, is the same property is applicable for square root of negative a into square root of negative b? By using this property, can we write as square root of negative a into square root of, that means negative b? If we can write like this, it is nothing but square root of negative into negative positive, a into b, ab. Let's we check, is it right or wrong? Let's. Square root of negative a can be written as square root of a into I. Square root of negative b is nothing but square root of bi. Now I want to find out square root of negative a into square root of negative b. Square root of negative a is nothing but square root of a into I into square root of negative b means square root of b into I. So square root of a into square root of b is nothing but square root of ab. I into I is nothing but I square. But I square value is negative 1. So square root of ab into negative 1. That means my final result is negative square root of ab. So from this we can understand that square root of negative a into square root of negative b is equals to negative square root ab. So please try to remember square root of negative a into square root of negative b is not equals to square root of ab. I hope it's clear. Now we are going to discuss what is mean by complex number and the definition. I will write the definition here. Let's see. Definition of a complex number. If a comma b belongs to real numbers, then the number of the form a plus ib, iota b, where I equals to square root of negative 1 is called a complex number. A complex number. Complex number, it is denoted or represented by z. That is z equals to a plus iota b. It is the general form of a complex number, where here a is known as real part and b is known as imaginary part. Real part of a complex number can be written as Re of z. Imaginary part can be written as Im of z. Please remember, Re of z means real part of complex number. Z means complex number. Imaginary part of complex number. Now, for example, z equals to 2 plus 3 iota, or z equals to 2 minus 3 iota. Or we can write, for example, z1 equals to 0 plus 4 iota. Or you can write z2 equals to 1 plus 0 iota, etc. These are the examples of complex numbers. Here I had to ask you one question. Is there any complex number if the real part is 0 or if it is imaginary part is 0? Let's see. For example, I am taking a complex number, z equals to 3. Can I write equals to z equals to it as 3 plus 0 iota? That means any number can be expressed as a complex number. in which the complex number is, the imaginary part is 0, then it is called as purely real. For example, Z1 equals to 3 iota. That means I can write 3 iota as 0 plus 3 iota. While observing, here, real part of complex number is 0. When real part of a complex number is 0, then it is called as purely imaginary. Now, so we can able to understand from the above concepts, every real number can be written as a complex number. When we can write every real number as a complex number, can I say that a real number is the subset of complex numbers? Is the subset of complex numbers. Complex numbers then generally denoted by capital letter C. If Z1 is a complex number of A plus iota B, and Z2 is another complex number of X plus iota Y. If Z1 equals to Z2, that means if two complex numbers are said to be equal, if and only if A equals to X and B equals to Y. That means if two complex numbers are said to be equal, if and only if their real parts as well as their imaginary parts should be equal. Now, there is one-to-one correspondence between set of all complex numbers. For example, in two-dimensional geometry is nothing but what? XY plane. If, for example, this is my y-axis, this is my x-axis. There is a complex number, for example, z equals to 2 plus 3 iota. That means here my real part will be 2 and the imaginary part will be 3. Both are positive, so I can plot as a point in my first quadrant. For example, it is 2, 3. For example, there is a complex number z equals to 0. 0 is nothing but what? 0 plus 0 iota. That means here real part is 0 and imaginary part is also 0. Then it will represent origin. That means this is the complex number. Similarly, if z equals to, for example, -2 -4i, then the complex number you have to represent in third quadrant. That is -2 -4. This is my complex number. That means it is -2 -4. This is 0, 0. That means you can understand that every point can be expressed as a complex number, and every complex number there exists a point in two-dimensional geometry. That's what I said. There is a one-to-one correspondence between set of all complex numbers. We know that 3 is a imaginary part of a complex number. 2 is the real part of the complex number. But 2 belongs to x-axis and 3 belongs to y-axis. That means it is x-coordinate, it is y-coordinate. That is the reason x-axis is called as real axis and y-axis is called as imaginary axis. I hope I am clear. Imaginary axis. Now, we'll discuss. Now, observe, there is, can we compare two complex numbers? Let's see. For example, Z1 equals to 5 plus 2 iota. Z2 equals to 7 plus 10 iota. If I ask you, is Z1 is greater than Z2 or Z2 is greater than Z1? We know that Z1 is exist a point in first quadrant, that is 5 comma 2, and Z2 is one more point in the first quadrant, that is 7 comma 10, because here x coordinate is 5, here y coordinate will be 2. Here x coordinate is 7, here y coordinate will be 10. There is no comparison between the 2 points. Am I right? We cannot say one point is greater than another point. So from that analysis, from the data, you can able to understand that there is no comparison between two complex numbers. That means if a plus iota b, if I was written as greater than x plus iota y, there is no meaning in this. Why? Points cannot be compared. We cannot compare the points. Now, we will do some operations on the complex numbers. Complex numbers. Let's see. We will do one by one. First one, addition. Addition of two complex numbers. Here, I will change my color. For example, Z1, I am taking A1 plus iota B1. And Z2, I am taking A2 plus iota B2. I want to find Z1 plus Z2. Z1 is nothing but A plus iota B1 plus Z2 is nothing but A2 plus iota B2. A2 plus iota B2. We can rearrange the terms here. A1 plus A2 plus iota B1 plus iota B2. We can rearrange the term. Observe here, A1 plus A2, if I am taking in one brackets, can I take common iota here? B1 plus B2. If I will take A1 plus A2, sum of two real numbers is also a real number. For example, if I am denoting by it as capital X plus B1 plus B2 is denoted by capital Y, here I. So observe X plus iota Y. It is also in the form of a complex number. So from this we can able to understand sum of two complex numbers is also a complex number. Complex number. Please remember, not only sum of three complex numbers is also a complex number. We do subtraction. The same one. Z1 minus Z2. That means A plus iota B. That means A1 plus iota B1 minus our Z2 will be what? A2 plus iota B2. Can I write it as A1 minus A2 plus iota times of B1 minus B2? Observe in the same pattern. The difference of two real numbers is a real number. Here also a real number. Suppose if I write it as A plus iota B. Here capital A indicates A1 minus A2. Let capital B indicates B1 minus B2. So now also you got in the form of a complex number. So we can able to understand the difference of two complex numbers is also a complex number. We'll do multiplication. Z1, Z2. Z1 is A1 plus iota B1 into Z2 will be A2 plus iota B2. Can I write it as A1 into A2 plus iota B2 plus iota B1 into A2 plus iota B2 by using FOIL method? So A1 A2 plus iota into A1 B2 plus iota into A2 B1 plus iota into iota square. Iota square means -1. So negative into positive, negative B1, B2. I want to rearrange the terms. By rearranging the terms, A1, A2 minus B1, B2, I can write. I want to put in a brackets. and here iota a1 b2 plus iota a2 b2. Can I take common iota? a1 b2 plus a2 b1. So can I write that as now z1 z2 is nothing but a plus iota b, where a is a1 a2 minus b1 b2, where b is a1 b2 plus a2 b1. So it is also a complex number. That means the product of two complex numbers is also a complex number. I hope it's clear. Now we want to do division of two complex numbers. Before going to division, I wish to give a small concept on conjugate of a complex number. If z equals to x plus iota y, or you can take a plus iota b, then the complex number a minus iota b, or I am taking here x and y, so I will write better x minus iota y is called conjugate of z, and is denoted by, that means conjugate of z is denoted by, and it is denoted by z bar or z power like a star. In generally, I am writing z upon a line. We can pronounce it as z bar. For example, if z equals to 3 plus 6 iota, then z bar equals to 3 minus 6 iota. For example, if z1 equals to minus 3 minus 4 iota, then z1 bar equals to minus 3 plus 4 iota. From this example, you are understanding that we are leaving the real part as it is. Observe here the real part is 3. Here also real part will be 3. But whereas the imaginary part here plus 6, here negative 6. That means if you are changing the sign of an imaginary part of a given complex number, then you will get conjugate of that complex number. For example, geometrically, let's observe what is the geometrical meaning of conjugate of a complex number. For example, here z is 3 plus 6 iota. I am writing for this 3 comma 6. 3 comma 6 is present in first quadrant, 3 comma 6. What is its conjugate? 3 comma minus 6. This point will be x coordinate is 3, y coordinate will be negative 6. So x coordinate is positive and y coordinate is negative, present in fourth quadrant, maybe here 3 comma minus 6. Try to understand that. Observe here. Can I say that it is means 3 comma 6 is the image of 3 comma minus 6, as well as 3 comma minus 6 is the image of 3 comma 6 with respect to x-axis. So try to understand here. The concept is conjugate of a complex number is image of that with respect to x-axis. Conjugate of a complex number is the image of that with respect to x-axis. I hope it's clear. There are some properties of there for conjugate of complex numbers. We will discuss the properties of complex numbers in my next video. Today, I am going to discuss division of two complex numbers. Let's see. For example, Z1, I am taking A plus iota B. Z2, I am taking C plus iota D. Just I want to find Z1 upon Z2. Here, my Z1 is A plus iota B upon my Z2 will be C plus iota D. I hope all of you know about rationalization. of a search. You learned in search how to do the rationalization. Here, I want to do rationalization. If you want to rationalize, just I want to multiply both numerator and denominator by c minus iota d upon c minus iota d. Now observe here, a into c, ac, a into negative iota d, that means negative I AD plus into plus iota b into c, that means iota bc. Now plus into minus iota into iota square b into d bd upon, just I want to do that. Here observe the denominators. It is in the form of a plus b and a minus b. So can I write directly a square? Nothing but here a square means c square minus b square. That means iota d whole square. If you want, I will write that the property a plus b into a minus b equals to a square minus b square, algebraic identities. Now observe here, can I rearrange this AC here minus iota AD plus iota BC. Here iota square is negative 1. Negative of negative positive BD upon C square. Iota square is what? Negative 1. So negative D square. Negative of negative positive D square. Observe here what I am going to do now here. That implies, can I write it as AC plus BD? Now, plus iota I am taking common, plus into BC minus AD. Can I write upon C square plus D square? Now, can I write it as AC plus BD upon C square plus D square plus iota times of BC minus AD upon C square plus D square. If I represent this AC plus BD upon C square plus D square as some letter A, capital, plus BC minus AD upon C square plus D square, if I represented by capital B, then it will be iota B. Now observe, you will get Z1 by Z2 in the form of a complex number. So what we can understand from here, the division of two complex numbers is also a complex number. Again, I am recapping what we are learning today, the properties, arithmetic properties of complex numbers, that is addition, subtraction, multiplication and division. Sum of two complex numbers is also a complex number, and difference of two complex numbers is also a complex number, and the product of two complex numbers is also a complex number, and the division of two complex numbers is also a complex number. And we learned what is meant by conjugate of a complex number. The conjugate of a complex number is nothing but just we have to change the sign of imaginary part. If for example Z is a complex number of a plus iota b, then its conjugate is denoted by Z bar. It is a minus iota b. I hope today's concepts are clear. I will do some problems and I will explain the properties of conjugate of complex numbers in my further video. So I hope you all clear what we discussed today. Thank you. Thank you to all.